Hey there, friends. Today we're going to be talking about the octal to decimal notes. When we enter into the octal world, what we're really kind of doing is looking at the world in a different base system. And so we will learn pretty soon about this thing called the octal base, which is the base 8 system. We have 8 digits that can represent our numbers. Kind of like binary, we had 2 digits that could represent our numbers. We will later on learn about hexadecimal, which is another base system that uses 16 different digits. A little funky system there. We'll kind of learn about that, though, at a later date next week. But for us, what we're going to focus on is how to convert octal numbers to decimal values. So we're going to pretend like that work on the right-hand side does not exist because I am right in front of you guys teaching you this lesson in person. So the first thing I want to talk about is this is not the number 270. This is the number 270 in base 8. And so this is what we would kind of represent it as, so we don't get it confused with the actual number we think of as 270. This is 270 base 8. Well, how do we convert this? We actually do a similar process that we used to the binary numbers. Each of these placeholders is going to be having a value to it. And the value to it is always whatever base we are in, raised to the 0 for the farthest right placeholder. And as we scoot to the left, each time we do, we raise that exponent to 1 larger than before. We can then calculate these values. Anything to the 0 power is 1. 8 to the first power is 8. 8 squared is 64. So these are indeed I would say, values or the worths of those particular placeholders. So when we look at this again in real life, we're always kind of talking about how this conversion works. You're saying that you have 0 things that are worth 1. You are saying you have 7 things that are worth 8. And you are saying that you have 2 things that are worth 64. You can see on the right-hand side, we are kind of performing these calculations right in front of your face. So if you look at this, we've got what I have highlighted in red here. I have 2 things that are worth 8 squared, or 64, that we see right there. I then have 7 things that are all worth 8. We get the 8 value from 8 to the first right there. And finally, we have, I did that, supposed to do that up here. Yeah, I'm not even highlighting right. And last but not least, we have 0 things that are worth 8 to the 0 power. We see that calculation occur right here. 8 to the 0 is the answer of 1. And so we combine all of these together, we do end up with a value of 184 in the decimal world. Again, using the same process we did for binary. This time, though, we have 8 different place values, and we realistically have only 8 different digits that we can use. So you'll notice that 7 will become the largest number that we see in these actual numbers. Let's try another one real quick. The value 777. In base 8, it's not 777, but we are going to convert this in the same exact manner we would have earlier. 8 to the 0 power, 8 to the first power, 8 to the second power, or 1, 8, and 64. I'm going to try and color coordinate this a little bit better this time. And I'm going to work from right to left. So the first thing we notice, I have 7 things here that are all worth 8 to the 0. Once again, I see that calculation there. 8 to the 0 is 1. I have 7 things that are all worth 8 to the 1 power. Look at this, guys. I'm getting good at this. And we finally have 7 things that are all worth 8 squared. Oh, almost messed that up there. That 8 squared is worth 64. And again, we see all of this fun stuff happening. I call it fun, at least. We end up with a value that is 511. This is our base 10 digit after adding and multiplying those together. I do want to show you this really quickly. You guys are not going to be able to be using a calculator on our tests. And something like this just might happen to make its way there, where you're going to have to hand multiply 7 times 64. Brief little reminder of how to do this. First thing I would do, write the larger number on top, smaller number on the bottom. This is some good old middle school math right here. So the first thing that we're actually going to calculate is the 7 times the 4. If you look at 7 times 4, we should get the answer of 28. The next thing we do is we have to take 7 times 60. So this is where you have to think of this as the number 60. And what we do is we kind of take this 0 and just utilize it down here to do some math a little bit easier. And so what I end up doing here is I'll throw the 0 in there, and I'll just multiply 6 times 7 and throw that value in front. Hey, 7 times 60 is 240. It's just a nice little trick that we can use to get that going faster. Add these values together. We end up with 448. I believe that is the same exact answer that we see right here. So that is a skill that you guys should utilize, because you never know when it might show up on a quiz for you guys. One thing to kind of keep in consideration, this is a weird thing that we see in any base that we have. What happens when we exhaust the largest values we can for octal? Remember, with octal, you get 8 digits, so you have the digits 0 through 7. Those are all 8 that you get to use. So we're maxed out here, maxed out here, maxed out here. What's the next number going to look like? Let's kind of take this into the decimal world real quick and take a look at what 999 would look like. What ends up happening here is once we've reached the maximum value we could for three decimal places, we're going to have to introduce a new decimal. So we're going to have another place value here. What happens with these? That 9 ends up reverting back to the lowest value that we have available, or 0. Same thing with this 9, converts to a 0. Same thing with this 9, converts to a 0. And then we have to add in the new placeholder. Did you know the number after 999 is the number 1000? Let's see how this works in the base 8 system, where the maximum that we have is 777. I've utilized the largest value 3 times in a row. Well, the same exact thing's going to happen. We're going to have to introduce a new decimal, or not a decimal place, a new octal place. The 7 turns into its lowest number, turns into its lowest number, turns into its lowest number. A new placeholder is put in here, and we end up with, whoa. The number that comes after 999 is 1,000, and the number that comes after 777 is 1,000? Not quite. These are base 8 numbers. So these are not 777. This is 777 in base 8. This is not the number 1000. That is the number 1000 in base 8. Weird to look at, but that is the logic that we're kind of utilizing in this situation. And we again see that right here. The number that comes after the number 777 is actually what looks like 1000, but those are base 8 values. Weirdly, if we converted those to decimals, those values are really only one number apart. Converting for these, the really only thing I wanted to point out for you guys was this one, how we would kind of utilize the same exact approach to this. 8 to the 0, 8 to the first, 8 squared, 8 cubed, 8 to the fourth. With this one, just remember though, you don't have to ever multiply out your zeros. So the only calculation that really has to happen here is you have one thing that is worth 8 to the fourth. And if we cheat a little bit and look over here, I think that's going to give you the value of 4,096. But again, we could multiply those in a very similar fashion as we did earlier. All right. The last thing I wanted to point out was this. A question might pop up somewhere where we say, if you wanted to store an octal digit, you have 8 different digits that you can use in octal. How many bits would we need for that? Well, I've highlighted here this hugely necessary formula that we're going to want to use. And what I mean by that is this formula is going to be on a lot of quizzes, a lot of tests going forwards. If you want to know how many unique or different values or different combinations you can utilize with a certain number of bits, we take the base that we are working in, base 2, we raise it to the number of bits, and that actually does give me the unique or the different number of combinations that I can make with those bits. And so in this situation, or this example that we see, we are now trying to figure out, well, how many of these base 2 values can I fit 8 different values, 8 different octal digits? So we're now looking for the smallest n value that can pass this assessment. What's the smallest element value that at least reaches the value 8? Well, I know 2 cubed is actually equal to 8. So that is the smallest value, and the smallest number that we can get to fit this equation, which means that we should be able to represent all 8 different digits with 3 bits. And take a look over here. If you look at all these highlighted sections that I have there, using 3 zeros and 1s, those are all the possible combinations that we can utilize with them. So it's kind of neat to see, but this is, again, something to put in the back of the memory bank. I think you're going to have to utilize this quite often throughout the year on MCs, again, on your AP exam. For the final thought, what is the actual algorithm that we use? Is there a pattern that we see happening when we convert these values from base 8 to base 10? Yes. You will recognize, especially if we look at one of these examples like these, this kind of math that you see us doing right here, we did this same exact stuff with base 2. The only thing that was actually different was what were the values of those placeholders. They're going to change now, but I think you'll see that in the algorithm, not much changes at all. But let's go ahead and run over to our computers. We're going to open up the base converter program, and we are going to write and hopefully finish the function base 8 to base 10.